Alright, so in this video, we are basically looking at optical activity and racemic mixtures. So let's begin with optical activity. So light has what? Two components, electric component and magnetic component. So light is an electromagnetic wave, and this is how it looks like. The electric and magnetic components are perpendicular to each other. So light rays basically move in all directions. But now, if we pass light, we should bring a filter in front of us, a light ray, and then we make sure that this filter allows only one component of the light to pass through. Look at how this filter is. So just imagine these holes are what? Vertical holes. So it's only this vertical component of the light that can pass through. So at the end of the day, this one, so all of them will be blocked. Only this one can pass through this filter. So we call this what? Polarized light. We've polarized it. So this is the actual thing. This is what? Plain polarized light. We polarize it. We make sure that this is only moving in what? One plane. And after that, we can put a tube here, and this tube will contain what? An a compound. So an enantiomer. Good. We put an enantiomer here, and at the end of the day, this light passes through this tube and comes out. It can be rotated to the right like this. If it's rotated to the right, we call it what? We say it is positive, and then it is also dextro rotatory. It can also be rotated to the left, and then we say it is negative, and we call this one out level rotatory. Then after that, we put another thing here to measure the angle. So this is calibrated in degrees to measure the angle of rotation, how this light has rotated. This will measure the angle. So this is called the analyzer. All right. So this is basically optical activity of enantiomer. So if this enantiomer is R, it can either rotate the plane polarized light either to the right or to the left. If it's to the right, then we say it is what? R what? Positive. If it's to the left, then we say that it is what? R negative. So if this enantiomer was also an S enantiomer, then and it rotated the light, the plane polarized light to the right, we say it is S positive. If it rotated it to the left, we say it is what? S negative. Take note that R and S has nothing to do with plus or minus. The fact that you are plus and meaning you are being rotated to the right doesn't mean that it should necessarily be R and not S. You can be S and you'll be rotated to either right or left. You can also be R and be rotated to what? Either right or left. R and S configuration is just to name enantiomers. Alright. For the rotation, it can either be left or right. Doesn't matter whether you are R or you are S. Take note of that. So this is optical activity, meaning enantiomers are what? Optically active. So one property of what? Enantiomers, they show optical what? Activity. They're optically active, meaning they can rotate plane polarized light. But how do they rotate it? To the same extent. If yes, if the R enantiomer rotates plane polarized light to maybe an angle of 25 degrees, then the S enantiomer will also rotate plane polarized light to the same angle of what? 25 degrees, but in opposite what? In opposite direction. So if the S is rotating it to the right, dextro rotatory, the arrow rotates it to the left, level rotatory. But all will be what? One will be positive 25 degrees, the other will be what? Negative 25 degrees. So this is another property of enantiomers. They rotate plane polarized light to the same degree, but opposite direction. The R and S enantiomer of the same compound, they rotate plane polarized to the same angle of rotation, but opposite direction. Whilst one is going level rotatory, the other is going dextro rotatory, but all of them the same angle. Good. So now, I even forgot to add this. This filter is what's called a polarizer because it's going to polarize the light, and this is polarimeter. Then this is analyzer. Then you observe at the back here. All right. So now, if the compound you have here is a mixture of 50% of the R enantiomer and 50% of the S enantiomer, what do you think will happen? Yes. So what will happen is that as the R rotates it level or let's just say level rotatory maybe 25 degrees, the S will also rotate it dextro rotatory 25 degrees. So at the end of the day, the plane polarized will come out unaffected. It will still be as it was like this. To come out like that because since the R rotated it to the left at 25 degrees, the S also rotated it to the right at 25 degrees, so bringing it back to normal. So R sent it maybe this way, this way, then S was bring it back to that way. So if you have a mixture which is of enantiomers, which are 50% R and 50% of the S, then we call this a racemic mixture. So that's why I say we are talking about optical activity and racemic mixtures. Racemic mixture means you have equal concentration of both enantiomers. So what if you have 70% of the R and you have 30% of the S? This is not a purely racemic mixture. So here, one of the enantiomer is in excess. So you can see enantiomeric excess exists. And who is in excess? The R enantiomer. So this is not a pure racemic mixture. If both concentrations are the same, then we say it is a racemic mixture. What if I put a substance here which is not chiral, achiral? If you are not chiral, you will not be optically active. If this substance was achiral, it will come out, the plane polarizer will come out unaffected. So this is all about optical activity. So enantiomers. All right, now let's see how can we separate enantiomers. So another property of enantiomers, we are seeing more properties. If enantiomers are, let's put them in two mediums. So the first instance, we'll put them in a chiral medium. And then the second instance, we'll put them was an achiral medium. Enantiomers have similar or same physical properties. Good. So if you put them in a chiral medium, they behave differently. They behave differently. If you put them in another chiral medium, they are already chiral. So if you introduce them into another chiral environment, they behave differently. So, but if you put them in an achiral environment, they behave what? They still behave the same as they were. So let's use the analogy of what? Like charges repel and unlike charges attract. Negative and positive always attract, but positive and positive or negative and negative will repel each other. So since they are chiral, you bring them to a chiral medium. No, they'll be different. But if you bring them in an achiral medium, they will still behave the same. So based on this, we can separate racemic mixtures or enantiomers. So we can use an achiral medium. We can also use an achiral amine. We can use what? A chiral amine. So let me ask, if you use um an achiral medium, can you separate them? I don't think you can separate them because they'll act the same in the achiral medium. If you use an achiral amine, you can't separate them. But if you use a chiral amine, you can separate them because they'll react differently. Now, we want to make this condition standard. So the wavelength of the light we are using, we want to get the wavelength of sodium. So we use a sodium lamp, which means we call something specific rotation. Wavelength is here, temperature is here, and it is equal to observed rotation all over what? Length times what? Concentration. Good. To get a specific rotation of what the plane polarized light, you need to know the observed rotation you observe here, whether you're 25 degrees, negative or positive. And then the length of this tube, your polarimeter, the length should be in decimeters. And the concentration of the substance here or compound there, it should be in what? Yes, your length of the tube in decimeters, your concentration in grams per milliliter. Then this is your observed rotation. So specific rotation means we are making things standard here. We are using a particular wavelength. This symbol is for wavelength, this is for temperature. So you can take a particular temperature like room temperature. So if you see specific rotation with D over here, meaning they are using what the D line of sodium lamp, meaning we make things standard here. So you can use this formula to calculate your specific rotation. So if any of these parameters is given and the other is not given, you can use the formula and you are good to go. This is optical activity. In the next video, we'll look at diastereomers, meso compounds, disubstituted cyclohexanes. Thank you.